Hey everyone, this is Angie with Angie's Beyond the Lecture. And this set of videos that I'm putting out today is covering major geometry concepts, and that includes circles and sectors and angles inscribed in circles, as well as polygons. We also have some similarity in quadrilaterals and some surface area and volume of solids. The first topic today is going to be basically the difference between a central angle and an inscribed angle, and then the rules that go along with it as far as math and geometry are concerned. The first thing we have here in front of me on the screen is going to be a circle. We'll call it circle C because we name the circles after the center point. So this is circle C, and we have a central angle inscribed within that circle. And the central angle essentially means, by definition, is that the vertex of that angle is sitting on the center of the circle, and then it forms an angle by extending out to two other points on the circle. So in this instance, this particular, it looks to be an acute angle. I didn't give it a value, so to speak, but we can go over an example real quick. Now, we gave this angle A, and the key thing to know here on a central angle, it matches in degrees the arc length that it intercepts. So what that means in plain English is that if we have an angle, say I'll give it 30 degrees. So I'm saying angle A is 30 degrees, and it intercepts, and I probably should put some letters here to be formal. We can call this A. We'll call this A, and this point B on the circle. So we can say arc A and B, and I usually just I'll squiggle that line to be explicit. That particular arc in the circle is arc AB. We note it like this, and it has a measure of, voila, 30 degrees. So I love it. Easy button here. Central angle is 30, and the arc that it inscribes is 30 degrees as well. So whenever you have a circle to solve, for instance, you would say, if you see either or assigned, so for instance, I could go backwards and say, well, I see this arc AB has 30 degrees. I can assign angle A, or actually it looks like angle alpha, is going to be 30 degrees for you there. Now, the difference between, I'll be back in just a moment. We have what's called an inscribed angle. I'm going to do this from scratch. One moment. Okay, so we'll give this point A on a circle. We don't need to be concerned about the center here, but I'll say we have point A on a circle, and I'll put B, C over here. Okay, so we have an arc. I'm going to use dashed lines because it'll be a little bit prettier here. Ooh, let's get that a little bit better. Lovely. So I have an angle A here in this particular situation. And we have arc BC. Now arc BC is just, simply point B to point C, and that's the arc that angle A intercepts. Now the difference between the central angle, relationship with its arc, its inscribed arc, we have angle A is actually half of what the inscribed arc is, okay? So think of central angle and its inscribed arc it's 1-to-1. So it's the same. We don't have to really think that one through. But here for arc BC, if I gave it, for instance, arc BC has an angle measure of 120 degrees, I have to work backwards and say, this is 60. This is something simple. A lot of these you can probably do in your head, or you can grab the calculator and simply either double or, double the angle, or to get the arc length, or cut the arc length in half to go backwards to the angle. But I wanted to point this out because it's a common things that students can mix up in their problems when they're solving circles. Now these are simply one angle type problem. You could have multiple inscribed angles and multiple central angles in your problem, and you just need to be aware of that. And those more difficult problems will be in a worksheet that I'll put out here on Patreon to kind of show you some more common examples that are a little bit more higher level that you might see. So we're on to the next problem. For this next problem here, we're looking at part 7, and this is the final section in my most missed problems review. So if we scroll up to the top here, we have several things covered here. Yeah, commonly missed questions and concepts. So we're looking at, actually, this is a bonus. I didn't put this in my original list that I put out last week, but I decided to add radians and degrees. So typically, radians are introduced in the trigonometry section, I believe, and that's going to be a second semester thing typically for geometry students. So traditionally, we learn about degrees. Angle measures are degrees, and we learn about acute and obtuse and right angles, and we can have anywhere from 1 degree up to a full rotation of 360, and we normally stop there. You can go further, but that's discussed later in upper level math and physics. And in geometry, they do introduce this concept where we have what's called pi radians. Actually, I need to switch this to pi pi radians here. So we have, and actually, I'm going to take this a step further and introduce the concept of radians, pi radians, and degrees. So we'll start here. I'm going to back up here and talk about degrees. We have pi radians. And then what we have is just regular radians, okay? And I'll explain the difference here. But these are the 3 common ways you're going to see angle measures. I'm going to separate this last one out. This is more of a higher, when you get into like advanced physics, like probably AP physics, or at least maybe honors or pre-AP physics, and of course college and beyond, right? Well, I'll talk about that in a moment. If we go back to degrees, and I'm just going to explain what a full rotation looks like. So a full rotation is, of course, a circle, right? It's going to be 360 degrees, okay? So that's going to be starting at the horizontal, which is right here. And pardon my circle drawing, but that's a full rotation, right? That's 360 degrees. We hopefully most students understand that coming into geometry. Now, when it comes to pi radians, okay, pi radians, a full rotation is 2 pi, okay? So I'm going to draw this again, 0 degrees. This is actually pi. So here's 1/2 rotation, and we do a full rotation at 2 pi, okay? So pi is actually 180 degrees, okay? So if I gave you a straight angle, I would say that's either 180 degrees, or I can say that's pi. And technically 0 degrees and 360 are essentially the same thing. They just form no angle, right? It's like the angles, the sides of the angles are sitting on top of each other. So 2 pi would be a full rotation, and it's essentially the same as 0 degrees. And that's what represents a complete and full rotation. And so your job is to understand basically here how we can convert between the two. Now, radians is actually just a raw number expression is how I would look at it. And so when it comes to a full rotation, you're really taking 2 times pi, which is 2 times 3.14, which equals 6.28. And of course, we know pi is, goes on and on forever. It's we just truncate it to 3.14 traditionally. And so I would say, full rotation from an angle perspective in radians is 6.28. Now that last section on the right, I mean, yeah, we don't, like if you were to give me, say, an angle of 5 radians, right? That's just a little hard to conceive. It's not 5 degrees, it's 5 radians. So I know it's somewhere between 180 and 360. Actually somewhere between 270 and 360. So what I mean by that is, I mean, yeah, you can kind of, if you're given radians here, which I wouldn't expect you, and I don't think your geometry teacher expects you to know this, but if I'm given 5 radians as an angle measure, I know it's somewhere between 90. I know it's somewhere over here in the fourth quadrant. I know it's between, this would be 6.28. This is 3.14. And so it's got to be, that's actually kind of hard to judge, between 3 and 6, 3.14 and 6.28. It's going to be to the right of 270, I think. Don't read too much into that, but just know what radians are, or just have a sense of them. Radians, just straight radians, would be just the raw number, okay? The raw number of that angle in terms of pi. But what we're dealing with in geometry is going to be, degrees and what we call pi radians, okay? So pi radians means we're going to have pi in our answer. So I won't belabor that anymore. We're going to go back and just basically live in the degrees and pi radians world. So if we go back here, I'm just going to delete this here. And I'll get rid of the radians. That was just kind of informational, a little bit extra. Your teacher might touch on it, and it's something you'll probably see later in your math and science career, in your STEM career. Now back to degrees and radians. So what I know, okay, so I know 360 degrees is equal to 2 pi radians. Like if I were to set up a ratio like that, so 360 equals 2 pi. And if I'm to, I could actually simplify that. Let's say 180 degrees is pi. Okay, so for every pi in pi radians, I have 180 degrees. And we use that ratio. In fact, you'll see that right over here. Boom, boom, boom. 1 degree is equivalent to pi over 180 pi radian. 1 pi radian is equal to 180 degrees divided by pi. Okay, so how does this work? How do we convert degrees to pi radians and then pi radians to degrees? It's actually quite simple. So for instance, if I give you, I'll just start, these are common angles right here. So 30, 45, 60, and 180 degrees. Those are all very, what we would call common angles that we work with in geometry and trigonometry. And so we'll just start there. If I have 30 degrees and I want to convert to pi radians, I would simply use the first ratio. 30 degrees times pi over 180. Okay. 30 goes into 180 how many times? 6. That's where we get pi over 6. Okay, pi over 6. And then we also have 45, 60, 180. They might throw at you, I don't know, maybe like 72 degrees. Something that's like divisible by 5, or something that's divisible by 6 or 3. I'm trying to think. Yeah, like 120 degrees. Pi over 180 degrees. So 120 divided by 60 is 2, and 180 divided by 60 is 3. Yeah. You're a little rusty there, Angie. 2 pi over 3. And you just do the opposite. So for instance, if I am looking at, I don't know, pi let's just look at something kind of not common like pi over 8 or something like that, pi over 8. Then I would say 180, 180 divided by pi. That's we're just flipping the ratio. Your option is going to be pi over 180 or 180 over pi, right? You have one of two options. And if you want degrees, you got to make sure pi's cancel, so put pi on bottom. So 180 degrees divided by 8, that's not going to be, it's kind of late for my brain to be doing math, so I'm just going to take 180 and divide by 8. Might be an improper fraction. I'm getting 45 over 2. Yeah, I guess you could divide 180 divided by 4. Yeah, so if you reduce, we can, of course, reduce here. 180 over 8. I get 22. I get 22.5. Probably taking this a little bit too far. A lot of times, teachers want a fraction, 45 over 2. Either one would probably do the trick here, but you get the idea. Let's do like 7 pi over 4. Okay. 7 pi over 4. And again, in geometry, I think the main idea is that you're just trying to get used to switching from degrees to pi radians and then back. I wouldn't worry about anything as far as angles are concerned. I wouldn't worry about anything, beyond a straight line of 180, right? So we do know in the angle world that, you can be acute or less than 90 in quadrant 1. You can be in quadrant 2 and be up to 180 degrees, right? And then in quadrant 3, you are between 180 and 270. And then in the fourth and final quadrant, you are between 270 and 360. All right. I just demonstrated that there on the bottom of the screen. Now, mostly in geometry, you're just dealing with angles that are between 1 and 180. All right. But they might ask you to, convert some higher angles. And a lot of this work down here on the bottom that you might be doing is more in like pre-cal and trig class, things like that. But back to 7 pi over 4, and I need to add my conversion here. So my conversion would be, my factor, right? Pi's cancel. Always make sure either degrees or pi's cancel. You have 7 times 180 divided by 4. This should come out nice and even. You get 315. Okay, 315 is going to be in that fourth quadrant. That's a rather large angle. And I hope this helps just going over converting from degrees to pi radians and then pi radians back to degrees. And then, of course, the concept of radians, you can completely ignore that. That was just sort of a sidebar conversation on what actual radians are and how they are, how they're measured, and just to give you an idea of what those are. Radians are typically used in physics when you happen to get into angular rotation, things spin around. And, that's something you may or may not see depending on how far you go in physics class. So hope this helps, and we're on to the next subject. There, so I am back in the next problem or section, and we're looking at pyramid geometry vocabulary, and I'll show a figure that demonstrates these different definitions. We'll start out first with a vertical or regular height. And that is defined as the perpendicular distance from the base to the apex or top of the pyramid. So that's the true height of the pyramid. We also have slant height. Warning, yes, it does have height in its name, but it's actually the height of the triangle that's slanted, from the bottom to the top towards the apex of the pyramid. That's probably why they call it slant height. And we typically call that S in figures, or sometimes L, lowercase l. And then we also have edge. So that's a segment where two faces of the pyramid meet. And I'll show you that here momentarily. And I didn't realize when I did this, when I constructed this pyramid, I don't have that back part. Oh boy. I don't want to interfere with anything, but yeah, there's a back side you don't really see, right, an edge. So we'll start with height of the pyramid. That's just the raw height from the center of the base all the way to the apex, all right? That's the true height. That comes into play when you're determining volume. Slant height, which I'm going to actually, I gave it S here. We can call it L, okay? We can call it equals L. And that actually, I'll put that in a better position. S equals L. And that's going to be running along the side from the middle of the base all the way to the apex. And it cuts these two, segments in half of the base. Okay, no, they're a triangle. Now an edge, I'll just use orange here for fun. And that's just where two faces meet. And you really don't use edge in problems. The only time you use edge is when you're using right triangle geometry to solve for a missing side. So they might give you an edge and maybe a base, and you need to figure out what the slant height is, right? Or they could give you the radius. I'll draw on the radius real quick here. The radius extends from the center to an outside vertex. Yeah. So some of these lengths, your segments are not, they don't lend to calculations of, say, volume or surface area, but they might come into play when you're doing actual calculations. For the purpose of this video, we're just going over the difference between height, slant height, and edge, okay? Because those are three very common definitions that get confused, okay? That get sort of get mixed up. So anyway, we have height, slant height, and edge. And again, height comes into play with volume. So for instance, if we were to do volume of this particular pyramid, I would do 1/3 area of the base times height. Okay, big B is area of the base. So assuming, I think I designed this as a square, we would just take side times side of the base and square it, and then multiply by the height, and then divide it by 3. You'll have your volume. For surface area or surface SA, we would do, again, the area of the base, and then we would also add 1/2 perimeter times our slant height. That's what you'll traditionally see in most books for the definition of surface area when it comes to a pyramid. And really we're just adding up all the triangles. So perimeter just represents each base of each of those triangles, and then we're taking that times the slant height and then multiplying by 1/2. So this essentially right here is area of a triangle, but we're simply adding them all together by using perimeter instead of just one base. Hopefully that's intuitive to you, and hopefully that describes the difference between height, slant height, and also edge. And I'll have more detailed problems in my handout that'll go over, finding perhaps the volume of a pyramid, and I'm given edge and maybe radius, or the base, the perimeter of the base or something like that. And I got to do a little detective work. You can't just plug it in and get the final answer for volume of surface area. You got to do some front end problem solving. So with that, we're going to jump over to the next topic. Okay, next up is going to be scale factors and ratios across dimensions. And we're just going to review first, second, and third dimension, what that relates to, and of course keeping our scale factors in mind and how we need to change those. How do we apply our knowledge of linear ratios and our linear scale factor, and then work it up to area and volume? Okay, so of course we know area is it's 2 dimension, and volume is 3-dimension, as I outlined right here in the handout. So yes, we have 1-dimensional ratios compare lengths, 2D are comparing areas, and then 3-dimensional ratios are comparing volumes. I'm just doing a comparison on cylinders, and if I were just to, I don't have values there, but I can easily say, okay, 2 and 6, 2 and 6, okay. So that's a 3-to-1 ratio, right? We know the, from a radius perspective, and we'll also do that here. We could do 6 and maybe 18 on the height. And we'll say this is, for instance, inches, just to give it a unit. Okay, so knowing what we know, 1D, 2D, 3D, or you could put length, area, volume, whatever your poison is, pick your poison. So we have 6 to 2, and I'm doing large to small, which is actually 3-to-1. So we have a 3-to-1 ratio. When it comes to surface area, we just have to square that scaling factor, okay, which is 3. You know, K is actually 3. Okay, the larger cylinder is 3 times bigger than the smaller. Now, here we have a 9-to-1 ratio. K is 9. And here we just cube that factor, or we can just simply cube each side of the ratio, and we get 27 to 1 as well. So K equals 27. Okay, so if we were to calculate out surface area and volume, we'll determine that the larger of the 2 cylinders has 9 times the surface area and 27 times the volume. So let's prove it to ourselves. We'll go ahead and do volume of A. And this is cylinder A. We'll just call this cylinder A. This is cylinder B. Volume of cylinder A is pi r squared h. So we're taking the base, the area of the base, and just multiplying it by the height to get our volume. Okay, so 36 times 18 is, whoa, 648 pi. Pretty big. Now, volume of B. Pi 2 squared times 6. Okay, 24 pi. 24 pi. So if we take 24 times 27, I do get 648. So if we're to take the ratio of volume A to volume B, that's 648 to 24. And yeah, I mean, that should give you 27 to 1. Yeah, 27 to 1. So if I just simply divide 24 into 648, you get a ratio of 27 to 1. I could, you know, if they said, hey, in these questions, they could just say, well, the 3D ratio, or no, they could say the 1-dimensional or linear ratio is 3, and then they give you the volume of the smaller cylinder. They'll just give it to you. They'll just assign a volume, and then you just need to know in this scenario that you multiply it by 27 to get the volume of the larger cylinder. Okay, so commonly missed is simply understanding the ratios and how they differ and how to apply them. Okay, and that's all for now. We'll go on to the next topic. Okay, next subject up is going to be composite solids. So composite solids are basically, and you can have actually surface area too. You can have composite 2-dimensional figures, but we're going to work with solids today. And we have an example of a cylinder with a hemisphere on top, basically a half circle. And, these are going to require multiple calculations and, remembering to, sometimes you have to exclude things when you're doing calculations, like you don't want to double count. So we'll go ahead and move over to the figure and I'll show you what I'm talking about here. Okay, so if we're looking at volume, actually volume tends to be a little bit more, it's a little bit more simple. We have a cylinder here and I have the formulas. There's our cylinder. There's the volume of our circle. All right, circle and cylinder. And I'm just going to give it a radius of, we'll just say, gosh, sorry about that, 4 centimeters. Okay. And we'll go ahead and use what's on the right here. Yeah, give myself some more room. Good. All right, let's use some pink, some dark pink. All right, and notice here the radius of the circle, there's symmetry here. We can use 4 centimeters on the cylinder as well. Pretend we know they're stacked on top of each other, and we can reasonably assume that the radii are the same for both the semicircle and the cylinder. So let's start off first here. And I need to give a height, don't I? I need to give a height. We'll say height is 12 centimeters. Okay, so if I start with volume of the cylinder, and we do know ultimately that we have, volume total equals volume of cylinder plus volume of our, I guess it's not really a circle, but we know it's a semicircular solid here. So we're going to have volume tote equals pi r squared h plus 4/3 pi r cubed. And I would just go ahead and plug in radius and height into each one. And we'll leave it in terms of pi. We won't multiply it out. So we'll have, for our grand total, we'll have pi times 4 squared times 12 plus 4/3 pi 4 cubed. Okay. We're probably going to have a fraction here. Now, 4 squared is 16 times 12. We'll have 192 pi plus 4 cubed times 4 divided by 3. Yeah, that is 256 over 3 pi. Pi over 3. Now, we could add 192. And, technically, in exact terms, we get 832 pi over 3. Are we done yet? No, I mean, we should leave it in cubed centimeters, okay? Centimeters cubed. Don't lose points. I mean, that might be a point or two off according to your teacher rules. So just be aware of that. I think that was one of our, I had that included in my original list that I put on YouTube that I'd be covering. Yes, don't forget, especially in the geometry when you're dealing with solids and whether it's surface area or volume, you'll want to make sure to include those units. If we're to tackle surface area as well, that might get a little bit more tricky. We'll do that just for fun. Surface area of a cylinder is going to be, we'll just have to watch. We don't want to count that top circle twice. So I would say surface area would just be pi r squared. Okay, instead of 2 pi r squared like the formula calls for, we'll just do one circle. And then the lateral height is just pi r h. Yeah, 2 pi r. Sorry, circumference of a circle is 2 pi r. And then we're just stacking a bunch of circles on top of each other to get that lateral surface area. So That would just be times the height. But don't forget the circle, right? So surface area of a circle is pi r. No, sorry, 4 pi r. 4 pi 4 pi r squared. Okay. But yeah, you know what? Yeah, that 4 pi r squared, if we're to chop it in half, it's not going to include that surface area of that half circle. So you know what? We're going to have to add in that 2 over here. We'll just include that. Actually, no, we don't. Because again, it's surface area. Never mind. Sorry about that. Back that up. Yeah. So for surface area of this particular solid, I just want to reiterate that we're taking the base of the cylinder, which is pi r squared, and then the lateral surface area of the cylinder, which is 2 pi r h, and then we'll just include half of our semicircular dome. So that would be 1/2 of 4 pi r squared. The surface area of a circle or sphere should be 4 pi r squared. And once we substitute, we'll have pi and 1/2 times 4 is 2 pi 4 squared equals. Okay. So we have 16 pi, 8 times 12. That's 96, right? Yeah, 96 pi. And 16 times 2 is 32 pi. All right, so 16 plus 96 plus 32 is 144 pi. And 144 pi, are we done? No, not quite, because we need to say, sorry, pi, centimeters squared. All right, now, again, composite solids really aren't inherently difficult. You just need to watch what you're doing as far as including or excluding sides like you should. So a lot of times in volume, you don't really need to worry about that, but in surface area, you do. And notice we excluded, instead of 2 pi r here, or 2 pi r squared here, I just took pi r squared. And that should get you to the right answer. So on to the next topic. Now, I believe this is the last topic here that I'm going over, and ironically, it's number 1. For some reason, I went backwards in sequence on this review guide. But I'm gonna, nonetheless, I'm gonna end with parallelograms and rectangles. So a few things. One thing that really stands out with the difference between parallelogram and rectangle properties now. So properties are things in quadrilaterals you just need to know. Now, I specifically isolated parallelogram and rectangle. There are other things you need to know, such as a kite, an isosceles trapezoid, a regular trapezoid, a rhombus, a square, and so on. But I just picked on the two most basic here. And what you all really need to understand is the first 5 are they're part of the definition, right? They're properties, and you need to memorize them, right? Teachers tend to quiz you on the regular on these in hopes that you'll remember them for the quizzes and exams. So we'll start off, we'll just go through that real quick. And then I have a pictorial on the parallelograms and the rectangles. So we can kind of go over some key mistakes. And the big mistake there between the two, between rectangle and parallelogram, is the fact that the parallelogram, the diagonals bisect each other, but they're not congruent to each other. Whereas in the rectangle, the diagonals bisect each other and they are congruent. And that's pretty handy when you're solving for various things here in those figures. So both pairs of opposite sides are parallel in a parallelogram, Both pairs of opposite sides are congruent to each other. We have opposite angles are congruent. Consecutive angles are supplementary. That's part of supplementary lines, and knowing that those same side interior are adding up to 180, and then diagonals bisect each other. So they cut each other in half, but they're not going to be necessarily congruent to each other. Now, rectangles, all properties of the parallelogram apply, except we have two additional criteria. All have to be right angles, and the diagonals need to be congruent, okay? So I had to draw these parallel or these diagonals in, so I apologize if they're a little wonky, but do know, for instance, if I were to give you, we'll just assume this is a parallelogram. All right, and so I'm going to say E. Yeah, this is E. All right, so if I know 6, and these are arbitrary, okay, and they want to know, for instance, they're just going to ask you, what is segment EC? What's the measure of that? And what is the measure of BE? Okay, so you can automatically say, well, I know this is congruent to that, and these two are congruent to each other, right? So AE is congruent to EC, and then BE is congruent to ED. So we know EC is 6, and we also know that AC would be a total of 12. And then we also have BE would be 7, because its corresponding part on the lower right-hand side is also 7. We also know that segment BT has a length of 14 units, okay? So this is a common example. When you're given parallelograms to solve, you might be doing angles and sides, but I'm just talking about the diagonals here in this case. If we go over to, I'm going to switch over to a rectangle. One moment. All right, so here's my rectangle. We will, you can assume it's a rectangle. And by the way, don't always assume, like, this clearly looks like a rectangle, right? They all look to be 90 degrees and opposite sides equal and parallel, but you need to be told explicitly or given enough information to know it's a rectangle. And we'll be going over more of that in my handout. So we have a rectangle here because I said so. And anyway, they could actually say, this particular scenario, we'll just give an A, B, C, D again, with the middle being E, and they might just give you 1, 8. But I do know that these all are equal to each other. Okay, they bisect each other and they're congruent. So I know this is 8, I know this is 8, I know this is 8, I know BD is 16, I know AC is 16, okay? And then EC was given at 8. I know AE is 8. I know BE is 8, and I know ED is 8. Okay? But we can't make that assumption in parallel, in the parallelogram. So I've noticed over the years when I'm working with students on this, they kind of hesitate. They're like, is the other side 8? You bet. EC is 8, and therefore AE is 8. You can throw in 8 and move on, or, indicate that AC is equal to 16. You never know what they're going to give you. You just got to work through whatever they ask you in these problems. So I hope this helps. This entire set of shorter videos helps with some common tricks in these particular sections. And again, I tried to do a survey of volume, area, some quadrilaterals, a little bit of polygons, right? Not too much on polygons here. And then I also did degrees and pi radians and so on. Just a nice little healthy mix of things you need to look out for in this section. This is typically second semester geometry material. And please like and subscribe if you want to see more videos. I'm trying to launch videos a couple times a week, as well as regular questions on YouTube on the community tab, and then some low-cost handouts on Patreon. So hopefully everyone, this is helpful to all geometry students coming in, and I'll see you in the next video. I'll also link some additional chemistry and geometry videos at the end of this. All right, thanks and have a good one.